Hi guys, it's GKCS. We'll be talking about persistent segment trees now. And in case you don't know about segment trees, you can check the link in the description. So persistent data structures are those data structures which can be queried for different times. Now let's say you are a person on Facebook and you have friends at time equal to 0 which count to 3. But at time equal to 1 you have 2 additional friends, so now the friend count is 5. But you lose a friend in the next second, so at t equal to 2 you have just 4 friends. So it was a little complicated scenario maybe, but the important thing is that you are changing the number of friends that you have, so your answer is changing at different times. But you might want to ask, at t equal to 0 what was the number of friends I had? And if you are just storing the newest information, then you just have 4 as your answer, but the answer should have been 3. So to answer these kind of queries, we need some sort of persistence, meaning that the data has to be persisted for the previous states also. So no modifications should be allowed for on the old data to add new data. That's the general idea of persistence. And persistent segment trees are just making those segment trees behave like that. So let's take an example of a list first. You have a list 1, 2, -1, 6, and these are the indices. If someone tells you to update -1, you don't just go and update this to, let's say -1 a of 2 has been set to 6 now. So instead of making this 6, what you will do is add a pointer to this node with 6 in it. So at t equal to 1, this is the new state, and at t equal to 0, this was the state. I think it was -1, yeah. So now you have the old information and the new information. If someone asks you at t equal to 1 what is at index 3, so you'll come here, you'll see there is no change, and you'll see 6. You can go back and till the point that you actually have a valid value. So this is a very simple example of persistence, just breaking ground here. And now let's pick up the segment tree. So as we know, a segment tree is a complete binary tree in which range queries from left to right can be answered in logN time. Usually there are just 2 kinds of queries that you have. One is update and the second one is query. So both of these are on ranges left and right. To save space, we won't mention it. Let's assume that these 2 nodes have to be updated. 0 to 1 need to be updated. So our standard procedure of updating a segment tree, we come to the root, we check if the range falls within this range. If it does, then query both nodes. So both these nodes are queried. This node says it entirely falls within my range, so it's going to return. This node says it doesn't fall within my range at all, it returns nothing. And so there's an update required here, there's no update required here, and there's an update required here. Notice that we are of course assuming there is lazy propagation, so these 2 nodes are not updated yet. In the standard segment tree, of course, these nodes will be updated, but in a persistent segment tree, what happens is at t equal to 0, the blue color is how the segment tree is. At t equal to 1, we draw it with red. Right. So at t equal to 1, we have these 2 nodes to update. And we have, let's say we have an array of root nodes. So at different times, what is the root node that you need to go to? So the first node needs to be updated. We create a new node with the updated value. This node also needs an update. So we create that node with the updated value. This node doesn't need to be updated. In fact, no other node needs to be. So for t equal to 1, we'll come here. Its left child should have been this, but it's been updated, so it will be this now. So its left child points here. Just reinforcing that left child thing. its right child doesn't need a new node. So we can just make it point to the old node. There's an update here, no updates here. It points to the old node. Now the old node does not need to have any further checks because it's the old node, so it has the same left and right pointers. This one needs to look at its left and right pointers. Its left pointer did not change, so we just make it point to the old left pointer. Right pointer did not change, we make it point to the old right. And so you see that this segment tree is the new segment tree that you need. But if you need queries for time equal to 0, you fall back to the old blue colored segment tree. What happened here is that you just needed logN nodes to be updated, because the segment tree has just logN nodes which need to be updated for a range query. You can guarantee that these operations will happen in logN time. So the update will happen in logN. Creating the additional nodes will happen again in logN. So that is logN time per query. If we add these two, then it's still order logN. And so you're still safe with the segment tree. For a query, well, depending on what time it is, you'll go to the particular route. Now the route may not change, so you can again make, this could have been pointing to this had the route not changed. So based on that, you will you'll query. You'll find out the route, and then in the standard segment tree procedure, go left and right if required. Right, so now we know about persistent segment trees. Let's solve a problem on SPOJ. Right, so we are going to be solving a problem on segment trees, persistent segment trees, using a SPOJ problem called MKTHNUM. It says that you have this array of size n, and what you need to do is you need to answer Q queries where there's a given range from I to j, and you need to find the kth smallest number in that range. So essentially they're saying that sort the array and then find the kth smallest number, but it doesn't really matter. Finding out the kth smallest number in a given range is an ON operation. So because you have Q queries, that will be in the brute force approach a QN operation. Too slow. Now, the first thing we notice is that if we have a segment tree, then we can answer a single query of this in just logN time. I'll just get some space here to prove that. Right. Let's say we have this array of -2, 6, 3, 12, 1, 18, or -18, yeah. So these are the indexes of the elements. Now, if we have a segment tree, I just said that we can answer this query in logN time. How? Firstly, we cannot use these values in our segment tree. So what we need to do first is map these values. Let's sort it. So we'll get -18, -2, 1, 3, 6, and 12. And for each value here in the new array, we use its index as the mapped value. So that is 0, 1, 2, 3, 4, 5. These are the values that you'll map it to. You'll realize in a second why this is the case. We are going to be using the frequencies of our mapped values in these nodes. That is 1, 1, 1, 1, 1, 1, 0, 0. 6 and 7 are not mapped to anything. 0 is 18's value. It occurs once. And 1 occurs once, and so on and so forth. The parents will store the sum of its children. So that's 2 here, 0 plus 0 is 0, 2 plus 0 is 2. Now that we have a segment tree, we need a strategy to traverse the tree. So let's have a query like 0, 5 and the third element in that range. So the entire range with the third element required. So we'll come to the root, and we'll understand if this root is the right element to look at. So how do we do that? Whatever is the value k plus 1 should be less than the element you're looking at, 6. K is right now 2, so is 2 plus 1 less than 6? Yes, it is. So this node has to be evaluated. We go on the left, we go on the right. First always to the left. We haven't gone on the right yet. 4 is what you're looking at. Is 2 plus 1 less than 4? Yes. So it has to be evaluated, we go on the left. 2 is the element you're looking at. Is 2 plus 1 less than 2? No. What does that mean? Well, first of all, k has to be subtracted by 2, because you have two elements here who are less than the person that you're looking for. So if the third ranked person is obviously behind 2 people, these 2 are those people, you need to skip them. And so you return from here, k is changed to 0 now, because it becomes 0. 2 minus 2 became 0. And we come here with k equal to 0. Here we check, is 0 plus 1 less than 2? This is the node that we're looking at. So is 0 plus 1 less than 2? No, it isn't. We need to evaluate it. We go on the left first. Is 0 plus 1 less than 1? No, it isn't. In fact, it's not even greater than 1. So it is exactly equal to this node. So this is the node that we're looking at. 2 is the answer for that node. So the answer for this query was 2, which in turn maps to 1. It was an entire chain. Now it might look silly, this entire operation was useless. We could have just come here and been like, okay, 0, 1, 2, and that would have been your answer. But not exactly. What if you had a value of 0 here? Your entire segment tree would change. This would become 1, this would become 3, this would become 5. And then the calculations would change, because you would have 2, yes, you would come on the left, and then the last element of this, which would be this element, would have been returned. So that's how the segment tree keeps everything flexible and is able to answer in just logN time what is the element at rank x for a given range. Alright. So now that we know that for a given segment tree and a given range, we can answer in logN time, let's try and reduce the number of segment trees we need to make. Firstly, if you have a sorted array of n elements and you try to insert a new element into it, it goes in at position p. Okay, sorted array, it went in at position p. If you add more elements to this array, then this index p can only increase. Why? Well, if all the elements that you added were larger, then p will remain the same. It will go in at the same position. If any of the elements were smaller, then p will shift to the right. But by how much? It will shift to the right by the number of elements which are smaller than the element that you are trying to insert. It's very important to notice that. So if we have, let's say, position, this gives you the value of p. Position of a element e from 0 to n elements, is always less than equal to the position of the same element e from 0 to from 0 to n plus x elements. If you added elements to this, x elements to this, the position should be greater than equal to what you had earlier. That's the claim. In fact, there's a stronger claim. Like we said, the difference in these positions is equal to the number of elements which were smaller than A of E. So in fact we have, so let's just minus position of this entire value, A of E 0 to n. This evaluates to position of A of E amongst these x elements. So that is n to n plus x. And if we just rename these variables, that will be n is I plus x can be considered as j. J is always greater than I, so. And here A of k. So this is what we are looking for. We wanted the position of the kth element. We want the value of the kth element at ij. Right. So this can be done fast. Why? Because instead of having segment trees for every I and j, you just need segment trees for every 0 to I index. So I ranges from 1 to n minus 1, 0 to, these are the ranges that you need to make segment trees for. So that's equal to n segment trees. 0 to 1, 1 segment tree, 0 to 2, 1 segment tree, up to n. Unfortunately, this also takes too much time, that would be n square operations, too slow. So we finally come to persistent segment trees. We take, let's say we take the first 4 elements and then make the segment tree. So minus 2 maps to 1, 6 maps to 4, that's here, 3 maps to 3, that's good, 12 maps to 5, so that is over here, and you have zeros here everywhere else. Your segment tree has these values in each of its parent. Like we expected, 4 elements at the top. Let us say you're taking the next element now. So that is this element 1. 1 maps to 2. So we can't update this value. We need to create a new node for this. 1 maps to 2, which has a frequency of 1 now. Its parent in turn changes to 2, with left child of this and right child pointing here. This parent again gets updated to 3 because its left child and right child are pointing here. 1 plus 2 is 3. And finally the root itself is modified because it has a right child here, 2 plus 3, which is 5. Alright. Now let's have a look at this. We want this second element in this tree for 2 time intervals. The first one is from 0 to 3. Find me the second element, index 1. And the second one is from 0 to 4. Find me the second smallest element here. Let's go for the first one, 1. 1 plus 1 is less than 4, we go on the left. 1 plus 1 is exactly equal to 2, we come here, this is your answer. For the first query, 3 is the answer. For the second query, 1 plus 1 is less than 5. 1 plus 1 is less than 5, 1 plus 1 is still less than 3, so we go over here, and 1 plus 1 is of course greater than 1, so we go back to the root, update that value, 1 plus 1 is less than 1, so the value is updated by 1, so this becomes, k becomes 0, we are looking over here 2, that is 0 plus 1 is less than 2, so we go down to the left, 0 plus 1 is exactly equal to 1, so we go to the rightmost child. This itself is a child, it doesn't have rightmost child, so this node has to be returned, index 2, and you'll see that that is actually the second element here. So what we have done is actually solve the problem MKTHNUM, which is highly discussed and it's a very interesting problem also. Not just because persistent segment trees are taught by it, you can also learn other techniques using this problem. But we have solved it in logN per query time. And to actually create these segment trees, you would need ON time. For each update, you would need logN time itself. So because you'll have n updates, you will be going through the array one by one. That will be n log n. So overall you have log n common n plus q total time. Plus n is asymptotically not so important. So this is the final query time that you need. And so persistent segment trees are rarely used, to be very honest, but it's problems like these which really bring the data structure to its height. If you have any suggestions or doubts, please leave them in the comments below. Also, if you have any suggestions for different data structures, please leave them in the comments below again. I'll be sharing all relevant description and links in the description below. So thank you, and I'll see you next week.